If you just look around you right now, chances are a camera lens is looking right back.
Oh, absolutely.
And I don't mean that in like a paranoid way.
Like,
It's just reality. We
yeah.
have drones mapping farmland from
Yeah.
miles up, security cameras on every corner.
Your dash cam, your phone.
The phone in your pocket has this insane camera. And then there's the really wild stuff, deep sea rigs, the Mars rovers, sending pictures back from other worlds.
Right.
So let's unpack that.
Yeah.
Because the sources we've got show that computer vision, or CV, isn't a gimmick anymore. It is everywhere, and it's doing things that, they were pure science fiction just a few years ago.
That's the core of what we're digging into today. We want to trace that entire history because the field accelerated so fast in the last, 10 years?
Oh, unbelievably fast.
It's easy to forget that the roots of all this go way back. Not to a silicon chip, but to neuroscience back in the 1950s.
So our mission here is really to connect the dots.
Exactly. From those first discoveries about how eyesight actually works in a biological sense, all the way to the multi-billion-dollar AI industry we see today, we're going to show you what those breakthroughs were and how the hardware finally caught up.
Okay, so where do we begin?
We have to start at the very beginning with the simple fact that machines couldn't learn to see until we figured out how we see. And that journey really starts in 1959 with two researchers, David Hubel and Torsten Wiesel.
And they were studying cats, right? The cat brain studies. This is kind of the origin story for a lot of deep learning architecture.
It is the biological blueprint. They weren't just watching, they were measuring brain activity, trying to map the first steps of visual processing. And they found two really important types of cells.
Okay.
First, they found what they called simple cells. And these were, they were incredibly specialized. They would only fire, only activate when they saw a line at a very, very specific angle.
So a simple cell is basically a tiny detector waiting for one single thing, like a perfectly vertical line in this one little spot, and that's it.
Exactly that. But then, and this is where it gets clever, they found complex cells. And these cells were getting signals from a whole bunch of simple cells.
Ah, so they're starting to build a hierarchy.
Precisely. The complex cells still cared about the angle of the line, but they showed something called translation invariance.
Meaning they could recognize the line even if it moved around a bit?
Yes. It didn't matter if the vertical line was here or a little over here. It still fired. And that layered idea, simple filters building up to more complex location-independent ones, that is the direct inspiration for the convolution and pooling layers in every modern vision system.
Wow. So once we had that biological model, the race was on to build it in a machine.
And it happened fast. Just 4 years later, 1963, a guy named Larry Roberts took a huge step with his work on machine perception of three-dimensional solids.
So he was trying to get a machine to see in 3D.
He was one of the first to really lay it out algorithmically. He showed you could take a 2D picture, find the edges, pick out the key feature points, and from that start to reconstruct the 3D object. It was a rigorous step-by-step process.
Almost like an operating system for seeing. And then institutions started getting involved, right? I see MIT's Project MHAY in 1966.
Right. They explicitly said their goal was to build a complex visual system that would be a real landmark in pattern recognition. The ambition was huge.
And this all led to David Marr's work in the 70s.
Yes, Marr's theory was a culmination of all this. He laid out this beautiful hierarchical framework for how vision works. It's still an amazing conceptual guide.
So walk me through that hierarchy. How did he think we build up a picture of the world?
He saw it as 4 stages. First, you have the input image. That's just raw light hitting your retina, pixels.
The raw data.
Exactly. Then the system creates what he called the primal sketch. And that's just finding the low-level stuff, edges, blogs, curves, the basic outlines of things.
Okay, that makes sense.
From there, you get the 2.5D sketch. This is a clever step. The system infers things like, which way is that surface facing? How far away is it? It's adding depth.
So it's not quite 3D yet, but is more than a flat drawing.
That's why he called it 2.5D. And then finally, the goal. The 3D model representation, where everything is organized into objects you can recognize. A chair, a table.
It's incredible. He was essentially proposing a functional algorithm for vision. And if you look at modern AI, that's exactly how they work. Layer by layer, building from pixels to concepts.
It is. The problem was Marr's theory and all that early excitement, it ran headfirst into a brick wall. And that brings us to the infamous AI winter.
Right. And this is where it gets really interesting, because the failures were almost as important as the successes.
They were. There was this huge excitement around these early models called perceptrons. But then in 1969, Minsky and Papert published a paper that just crushed that optimism.
They found a major flaw.
A crippling one. They showed that these single-layer perceptrons couldn't learn a very simple mathematical function called XOR, exclusive OR.
Okay, for anyone who's not a computer scientist, why was failing at something called XOR?
Yeah.
Why was that such a disaster?
It's because XOR is a simple problem that isn't linearly separable. So think of a perceptron as just drawing a single straight line on a graph. It can easily separate dots if all the yes answers are on one side and all the no answers are on the other.
Right.
But the XOR problem, it requires like a curved line to separate the answers correctly. A single straight line just can't do it.
So the realization was, if our most basic AI building block can't even solve this simple logic puzzle,
how could it possibly handle the messy, complex, nonlinear real world?
Right. And that skepticism it set the field back for decades.
It did. But even during that winter, some really important work was happening quietly in the background. Specifically, the neocognitron from Kuniko Fukushima in 1980.
And this model was directly inspired by the cat studies by Hubel and Voisel.
A direct translation. It was basically a prototype for a modern convolutional neural network, a CNN.
Built right in the middle of the AI winter.
It's incredible. It had layers of what he called simple cells, which we now call convolution, and complex cells, which we call pooling. It proved the biological idea worked in a computer, even if the computing power and the data just wasn't there yet.
Which brings us to the next key ingredient.
Yeah.
The data.
You can have the most brilliant architecture in the world, but if you only show it 10 pictures of a cat, it's not going to learn what a cat is.
And the sources all point to one thing as the tipping point for data. ImageNet.
Without a doubt. The ImageNet project, which started around 2009, changed everything. They built this massive, high-quality data set of millions of hand-labeled images. Finally, you had enough fuel to power these really big, deep, complex architectures. The stage was set.
And then, around 2012, the dam just broke. We entered this explosive growth period we're in now. What was it? What was the spark? It wasn't just the data. It had to be the hardware, the raw muscle.
It was a perfect storm. You had the data from ImageNet, and you finally had the hardware, specifically GPUs, graphics processing units.
Which were made for video games.
Exactly. But it turns out the kind of math you need for realistic graphics is very similar to the math you need for deep learning.
Let's talk about that metric, GFLOP per dollar, because that really tells the story.
It really does. So a GFLOP is a billion floating point operations per second. It's a measure of raw calculation speed. And if you look at the price performance, how many GFLOPs you get for your money, the GPU curve just goes, well, it goes exponential in the 2010s.
Because they're parallel processors.
Right. They do thousands of simple calculations all at once, which is exactly what deep learning is, just millions and millions of matrix multiplications. It was the perfect engine for the job.
And it's wild how fast that hardware evolved. AlexNet, the model that really kicked things off in 2012, ran on a GeForce GTX 580, a powerful gaming card for its time.
And today, modern cards have specialized hardware called tensor cores. These aren't for gaming at all. They're built for one reason, to make deep learning math go faster.
Okay, so break that down. What does a tensor core actually do?
Well, a tensor is just the main data structure in AI, a big multi-dimensional grid of numbers. Training a network means multiplying these huge tensors together over and over again. A tensor core is a dedicated piece of silicon that does that one specific job matrix multiplication insanely fast.
Like a specialized coprocessor just for AI.
Exactly. And once that infrastructure was in place, the industry growth was. It was immediate. You see this huge spike in AI startups right after 2010.
The numbers are just staggering. The sources here project enterprise AI revenue to pass $31 billion by 2023. This isn't just a research project anymore.
No, it's a pillar of the global economy. And you see it in academia, too. Conference attendance for places like CVPR and NeurIPS it skyrockets around 2014, 2015. The field went from a niche to the absolute center of computer science.
And we have to give credit to the pioneers. The Turing Award in 2018, the Nobel Prize of Computing, went to Hinton, LeCun, and Bengio for this work.
And it didn't stop there. This year, 2024, Hinton won the actual Nobel Prize, but in physics. That shows you how fundamental these ideas have become, connecting neuroscience, physics, and computer science.
So now we get to the really fun stuff. We're moving beyond just asking, is this a cat or a dog? We're in an age of interpretation and creation.
It's a total paradigm shift. Think about image captioning, which took off around 2015. Suddenly, a model could look at a picture and generate a whole sentence describing it.
Right, not just cat, suitcase, window, but a cat is sitting on a suitcase on the floor next to a window. That implies it understands relationships.
It requires reasoning.
Mm.
But the next leap is where things got, well, they got wonderfully weird. The era of generative modeling.
You mean things like style transfer in 2016, where you could take a photo of, say, your dog and have it repainted in the style of Van Gogh's Starry Night?
That was a huge step. It showed the machine could separate the content of an image from its style. But the real explosion was text to image.
Day A2. That's what really caught the public's imagination in 2021. The prompts were they were amazing. An armchair in the shape of an avocado.
Or teddy bears working on new AI research underwater.
I mean, how does a machine even begin to comprehend that, let alone draw it? It's not just finding a picture online, it's creating something entirely new.
It is. And the main technology behind this is something called a diffusion model. The best analogy I've heard is to think of it like a sculptor working backwards.
Okay.
So it doesn't start with a perfect block of marble. It starts with total chaos. An image of pure random noise, like TV static.
The raw material.
Exactly. And then, step by step, the model is trained to remove just a tiny bit of that noise. It makes a guess. This noise looks a little bit like it could become a face with a cowboy hat. And it nudges the image in that direction. It does this thousands of times, slowly refining the static until a perfect, coherent image just emerges.
That is an incredibly powerful idea. And it scales so well because it doesn't need a human to label every single step.
Which brings us to the big question. What does all this power mean for us? It's a double-edged sword. There's immense potential for harm and immense potential for hope.
And the harms are already here. These systems are making life-altering decisions. The sources point to that Washington Post article about HireVue, using a face-scanning algorithm for job interviews.
That's a perfect example. The system analyzed a candidate's facial expressions, their tone of voice, their little micro-movements, to decide if they were a good fit for a job.
And outside experts looked at this and called it profoundly disturbing.
They did, because they saw it as essentially pseudoscience, making huge decisions about someone's livelihood based on a black box algorithm that might be biased or just plain wrong.
And that's the real challenge, isn't it? Bias. These systems learn from the data we give them, and if our data has societal biases baked in,
then the algorithm will learn and then scale up those same biases. But on the other side of that coin, you have these incredible applications in health and safety that are already saving lives.
like the monitoring systems in senior care.
Yes. It's such a great example of scalable, low-cost, and burden-free technology. Instead of an invasive device, a simple camera can monitor for falls, check on sleep quality, even notice changes in diet or mobility over time.
You could provide early warnings for chronic conditions.
Or even something like COVID-19, just by detecting subtle changes in posture or movement. It's a continuous, non-invasive safety net.
It's just an incredible journey.
Yeah.
From studying a cat's brain in 1959 to specialized hardware like tensor cores to a $31 billion industry just 60 years later, the speed it's breathtaking.
It is. And yet, for all that progress, we're still a long way from true human vision.
Yeah.
We can generate amazing photos, but machines still struggle with context, with ambiguity.
Right. A human can walk into a room and instantly feel the subtle social dynamics. A machine, it's still just processing pixels.
It's getting better, but we're not there yet.
So, looking back at our mission, we've traced the line from biology to the chip and to the boardroom.
We have. And the field is moving so fast they keep inventing new names for things, like generative and interactive visual intelligence, just to describe what they built last year.
So what's the final thought we leave people with?
I think it's this. The hardware is getting exponentially better. The research is accelerating. CVPR, that main conference, got over 9,000 paper submissions last year. The technology is not slowing down. So the real question for you to think about is this. How fast will the ethical challenges, the questions of bias, of jobs, of privacy, outpace our ability as a society to govern them? That gap between technological speed and regulatory wisdom is the defining challenge of this entire revolution.